I want to start with a small warm-up. So we defined covariance. What was it? If I have two random variables, x and y, I look at the expectation of x times y, then I say minus x alone times y alone, and look at the difference. If this is a positive number, we say they are positively correlated. They kind of want to happen together. If it is a negative number, they don't like kind of repel each other. Okay, so we say negatively correlated. If this is zero, you're not able to say much. If x and y are independent, this will be always zero. But this being zero does not imply they are independent. It's not two-way, it's just one way. And quite often, this will be normalized. So you will take that covariance and multiply it with the standard deviation of the first one times the standard deviation of the second one. Then this way, you will get a number between -1 and +1. And I'll probably put it as an exercise for you to think about why this is between -1 and 1. That will be correlation. And now let's work on something else together. Let's say I got two random variables and I sum them. X and y, I sum them, okay? Then I want to understand what happened to their variance after I sum them up. So what was variance for a single random variable? One intuitive picture that you should keep in mind if your random variable, say, has a nice finite mean, then let's say if it's Gaussian, this peak here, the spread of the peak is going to be like standard deviation, more or less. So that's variance is square of the standard deviation quantity. So for a single random variable, variance kind of measures how much deviation you have from your average. Okay. Now what we want to understand is I took two random variables, summed them up. What happened to their variance? So this is a legitimate question because sometimes the variation between two random variables start canceling each other. You might add them and you might literally decrease the variation. It's kind of counterintuitive in this sense. Well, before you think about it, my gut instinct would say there is one variance in one random variable. There is another one with some variance. If I sum them up, it should be even more random. Like I should have more variance. But this doesn't always happen. Okay, and you can capture what happens precisely. And I would like you to think about a couple of minutes. It's literally algebra. Look up the definition of variance in your notes, plug it in here, then do the little algebra. You'll hopefully see this is the identity. Okay. And when you see this, this literally tells you what happened to the variance when you add them up. If this is positive, you increase it. If it is negative, you decrease it. If it was zero, then not much happened. You just add them up. Yeah, it's a good thing to do once. So think about it a minute or two. You don't have to finish or complete. It's good to think about it. Then we will move forward to the other stuff. And if you forgot definition of variance, it is literally take this covariance expression I gave you, put the same thing twice. Covariance of x and x will be the variance of x. For people who arrived a few minutes late, this is what we are thinking about now. Good. Let me maybe start plugging in the definitions. You don't have to look at what I'm writing. I'm just going to write the definitions. I think I warmed you up enough. Let me not take more time in lecture, or you guys are working. I'm feeling bad to interrupt. Yeah, but also for time purposes, I think you guys are warmed up now. So let's just look at it together, and then you can complete after lecture. So, what is the definition of variance of a random variable? In this case, it's x plus y, right? You take square of your random variable expectation. Then you take expectation of your random variable, you square it, you minus. Okay, that's the definition of variance. Maybe if I zoom out, if you see two things together, maybe it makes more sense. So variance of a single random variable x, expectation of squared, minus expectation of x squared, right? So here, instead of that x, I'm just going to write x plus y. That's my random variable now. Then I'm going to expand out. So x plus y squared, what is it? A plus b squared, or x plus y squared. X squared, 2 times xy plus y squared, right? And then expectation itself is linear. Expectation of x plus y is the same thing as expectation of x plus expectation of y. You have a parenthesis still, and then you have a square of it, right? But you can still expand it again. This is your a, this is your b. A plus b squared will be again a squared to ab, b squared. And if you do the algebra, this is what you get at the end. Okay, do this later. It's good to do it at least once. At the end, what you get is when you sum up two random variables and look at their variance, you get variance of the first one plus variance of the second one plus 2 times of their covariance. Okay, so if this covariance is 0, for example, in the case they're independent, there will be no covariance. If it is 0, then it's super nice. It's very easy. Then variance x plus y is just variance x plus variance y. That's the easy and nice case. The other cases make sense too. If covariance was negative, that means when I add them, the deviation from their average is actually decreasing. They start canceling each other. Okay? And if it is positive, they give you even more variance. Yeah, very good. So now, in the case they are independent, you're just summing them up, right? And that's the case you will use a lot all over the place. Now, last time I told you, okay, I showed you this, like, what was it? Data source pictures, like the statistics doesn't always tell you too much. But I also promised I'll at least tell you some of the stuff you learn out of statistics. So far, what are the statistics we are using about random variables? We take their average, and we look at their variance and standard deviation. That's the stuff we are using most. And I showed you these pictures. They have the same variance, same correlation coefficient, whatnot, and the pictures are totally different, right? This was to warn you against just looking at mean and variance and like conclude you know everything about random variable. But it still does tell you some stuff about your random variable, okay? So what does it tell you? One basic tool is called Chebyshev's inequality. How does that go? You got your random variable x, and you know its average, expectation, and you know, suppose its variance is a number. It's not infinite, it's 5, 10, whatever it is, okay? Then if somebody asks you, what is the probability of your random variable x? minus the average, absolute value being bigger than t. Let's see what does this mean. So let me try to picture. So let's say this was my real line. This was my average. And then here's lambda plus t. Here's lambda mu plus t, mu minus t. And then now we are asking the probability of being outside of this bracket. This is what this thing here is telling you. Okay, what is the probability of going a little away from your expectation? Okay, this is what this means. X minus this absolute value being bigger than t. It means either you're t or more, or t or more or less. Okay, that's what it means. And what is the probability of this? Turns out it is variance of x divided by t squared. So if you know variance is a small number, if you ask me what is the probability of being, say, 10 more than my average, it will be variance divided by 100. Yes, less than equal sign, this one. Yeah, exactly. So this is less than equal. Okay. So how did this look like? What? Okay, it is at most. Okay, I'm sorry. Thank you, John. Yeah. So it is at most this much. That's what it says. And so this way, your variance controls a little bit about how your random variable behaves. If variance is small, you don't expect it to deviate too much from the expectation. Okay. And now, if you remember, we were talking about something called law of large numbers last time. How did that go? You took a whole bunch of independent random variables. Suppose their average is the same. Okay. And then you only need to know variance is a bounded number. Suppose it's 1 for the sake of ease of discussion. And I sum them and divide by n. I'm taking average of my random stuff. It's very reasonable. Then what happens is that as n grows, probability of this guy moving tiny bit away from the expectation goes to 0. So if you look in terms of the tool I just showed you, like going t away is less than equal to variance divided by t squared. How does this look? This is saying it's literally going to 0. I know something about this probability. Let me circle back to Chebyshev. So I know that thing is less than equal to variance divided by t squared. And in the law of large numbers, this probability is literally going to 0. So that means like this right-hand side is going to 0. And this literally means your variance is probably going to 0. Okay? Now let's see if we can justify that's the case. So if you look at this random variable and try to compute its variance, what happens? So we know they are independent, so the summation is going to go nice. Okay? So let's do the variance computation. So variance of this x, I'm computing variance of this guy. Let me write with a different color. Variance of x1 plus x2, xn divided by n. So first things first, if you're dividing a random variable with n, the variance gets divided by n squared. So let me write it up. So this will be the same thing as 1 over n squared, variance of the summation. So far, so good. Since variance is squared thing, if you're multiplying a number by 5, the variance gets multiplied by 25. Okay, so that's all I'm doing. So dividing by n is same thing as multiplying by 1 over n. So the variance has got to be multiplied by 1 over n squared. Okay, how about this part? Since they're independent, variance of the sum just gets split up. It's going to be 1 over n squared. Variance stuff will be summed up. And we know those variances, they were 1. So I'll get 1 plus 1 plus 1 plus 1. independent. Yeah. Otherwise, you have to be careful about covariance as well. But here, since they're independent, 1, 1, 1, 1, 1, I get n of them, n divided by n squared, 1 over n. And literally, as n grows, 1 over n is going to go to 0. So this means if you have a whole bunch of random stuff, and they're reasonable random variables in the sense that they have an expectation and their variance is bounded, okay? And if you keep summing many of those and take their average, after some point, your random system will start looking almost deterministic. You'll start not seeing any randomness at all. Because look at the result. Probability of going tiny bit away from your expectation goes to 0. So you're always going to get a number around this. Yeah. And this does happen in systems that has a lot of randomness in. Yeah. Like, say, temperature of a room. It's average notion of an energy, and all these particles are moving around. And we can measure the temperature. It's actually a random thing, but it feels deterministic. Okay. So, yeah, so this does happen. And this was one thing we saw last time. And then we also see the central limit theorem, which was not dividing by n, but it was dividing by square root of n. Right? In that case, if you run the entire computation once again, you're not going to have like 1 over n squared, then you're not going to have this. If you would be dividing by root n, in the end, you will just get 1. So this variance squeezing is not going to happen. But then something interesting happens, you end up getting Gaussian. That's what central limit theorem was saying. Okay, so that's some recap of whatever we were doing last time. Now let's go on to do multivariate stuff today. And this should be more or less the last probability lecture we will do. Next lecture, we will do what's called decision theory, basically like basics of decision making. And then we will move on to neural nets next week. Okay, so we did, the stuff written here is about 2 random variables, x and y, and this is what we have done already. Now think about doing the same thing with many. Your x is a vector, it's got a whole bunch of coordinates. Your y is a vector, got a whole bunch of coordinates. And then define the same covariance again. But this time, since they're not numbers, I cannot multiply x and y. So what do? You either write x, y transpose, or literally you're doing a dot product. 2 vectors, how do you multiply them? Take their dot product. Okay. And then here again, expectation of x is a vector. This is a vector. Do their dot product. Okay. So at the end, I'll show you in more detail. Let me maybe, okay, I see that I lost a lot of people. So let me show one example of this multivariate thing in my empty sheet, then I'll get back to there. So how it's going to go is like this. And that product was a wrong sentence there. I apologize. So let me correct it. So let's say I got 2 vectors. Y happens to be 1, 1, 1, and x happens to be this 1, 2, 3. And when I write y transpose, it looks like this. So how this is going to go? You're going to multiply this 1 with this 1, and you're going to put it right here. And then you're going to multiply that 1 again with this 1, put it right here. Put it right here, right? That's what you're going to do first. Then you're going to go to the second entry, 2, multiply it with everybody, put it here and there. And this is what x, y transpose is. So x is a 3 times 1 vector. Y transpose is a 1 times 3. So this, what you get is 3 by 3, okay? So this is a matrix, okay? Now I said it right. So that's how the definition I was writing goes. So you got a matrix right here minus another matrix. That's the definition of covariance when you got 2 random variables with a lot of coordinates, right? And then sometimes you will see it written this way. This is going to be an n by n matrix. You can see it coordinate by coordinate as well. Look at the first coordinate of x. look at covariance of that first coordinate with the first coordinate of y, put it here as a number. Look at the first coordinate of x, look at the second coordinate of y, take their covariance, put it here as a number, okay? Now you fill this n by n. That's what covariance means for multivariate situation. So tell me the question, probably. Yes, for now, the definition would usually go by the vectors of same length. The question is like, if I got two vectors with different length, what do I do? So the standard definition is this, but if you want to do some computation in practice, you can add zeros. But this is the definition you would see everywhere, okay? They will be same length, very good question. Okay, now, one thing you would notice is since covariance x1, y2 is the same thing as say y2, x1, this will be a symmetric matrix, okay? So taking say first coordinate of x and the second coordinate of y, 1, 2, is the same thing as 2, 1. So you will get a symmetric matrix off of this all the time. All right, fine. Just like we did with one variable, you could also plug in x and x itself. I gave you the definition with x and y. What if I just plug in the same thing twice? Okay, x and x. Then you will literally be talking about correlations between the coordinates of your random vector. I took the first coordinate of my vector. I'll look at the correlation with that guy with the second coordinate. That's covariance of 1 and 2. I put it right here. So this whole matrix will literally record the relationship between coordinates of your big random vector, okay? And this is called usually covariance matrix of a random variable. When they write just co and x, that's what they mean, okay? And then you will see like a big matrix that is supposed to record how the coordinates are related. And so if, say, coordinates are all independent, what would you see here? Yeah, go ahead. Yeah, right, because independence means no correlation. So there will be 0, 0, 0 all over the place, except the diagonal. And in the diagonal, you will see whatever variance they got. So that's the nice case, right? If it is not independent, you will see some sort of correlation there, okay? Now that we know this definition, so I'm not gonna go through it because of time reasons, but this is now an n by n matrix. It is symmetric. So we know all eigenvalues are real. Can they be negative or not? Because of the structure, the eigenvalues of this guy will be always 0 or positive, which is also known as the PST matrix, okay? This is important, is used in computations all the time, but I will not show you why it is, which is right here. Well, I'll give it as an exercise. Okay, now let's go back to PCA we learned with this perspective. Now that we know how to talk about, covariance of random variables with many coordinates, let's try to go back and remember what we were doing there. So in PCA, we got data points. We used to have capital N, many of them. And every data point is a column here. They got N features, okay? Then we stack them together. We create the matrix, N by capital N. Then what did we do, if you remember? We took X transpose. So you're multiplying this matrix with its transpose. So it's gonna look like now N times capital N, then capital N times N. At the end, this whole thing is an N by N matrix, right? And if you go through the exercise of doing the algebra and whatnot, you'll realize this is essentially more or less covariance matrix of your data. Okay. So when you look at this matrix, you will see, if I would look at first coordinate of all my data, second coordinate of all my data, try to look at them in an aggregate way, how are those coordinates related with each other? This is what this matrix is supposed to tell you. Then what did we do? We took this guy with it, since it is positive semi-definite, you can write it this way. This is like singularly decomposition. In singular decomposition, you have U diagonal B. You can even write it the same, doesn't matter. And then we took the biggest singular values there and picked those directions. Let's say if I'm picking D dimensions off of my PCA, that means you're picking D columns from this U. And that means you're literally picking D directions that preserves most of your variance. You look at the directions, let's say I'm going to pick 5 of them. I'm going from n features to 5 features. This gives you 5 vectors. And if you go in those directions, that's where most of the variance happens. That's where most of the varying in your data happens. So when you preserve that, you're preserving most of the information given by your data. Okay. So PCA can also be obtained as an optimization problem. Give me the directions that preserves most of my variance. We obtained it by fitting the best subspace. You can do it this way, you will get exactly the same thing. Okay. So far, so good? Okay, so this is what PCA was. Now, we can also look at maybe probabilistic PCA. Well, before doing that, let me define what's a multivariate Gaussian. The thing you would see used most often as a random variable, as a random vector with like a whole bunch of coordinates is going to be normal random vector or Gaussian, random vector or multivariate Gaussian. It all means the same thing. What does it mean? You get a vector where all these coordinates are a normal random variable themselves. That's what a multivariate Gaussian is, okay? And then if you take the average of these stuff, it will give you n numbers, average of expectation of first coordinate, second coordinate, yada, yada. That's the expectation of this guy. And you can take the covariance matrix. So in this case, we are talking about when they're independent and variance is 1. And that corresponds to covariance matrix literally being identity. Super nice, okay? So that's the base multivariate Gaussian. Of course, you can do more complicated stuff. You can shift them, you don't have to take variance 1, you can take variance 10, okay? So this is the most basic one, where every coordinate is a Gaussian with expectation 0, variance 1. Okay, very good. And then since it's independent, the density factors out nicely. You can write it up. It's going to come out as something like this. Okay, it looks a little bit of a mouthful. But literally what I'm doing here is like density of the first coordinate times density of the second coordinate times blah, 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 density of the last coordinate. Since I assume densities are independent. Okay, yes, go ahead. So variance is assumed to be 1. So it's right here. 2 times 1 is 2. So you would see also variance here if there is a variance. Okay. The only difference is when you're doing density of a vector, you need to ask density around a vector. For univariate Gaussian, you ask, tell me the density of Gaussian around 10. Right? But if I'm talking about multivariate, what does it mean to ask a vector around 10? You have to tell me density around the vector itself. So you give me the vector you like, and I compute the density. I'll give you some pictures, and this will be visualized better. For now, I'm just defining. And if the definition is looking kind of too technical, don't worry. You don't have to memorize this stuff, okay? You just need to know what's a Gaussian. Okay, fine. And this is the case, as I said, when every coordinate is independent and they are mean somewhere and variance 1. All right, and okay, I'll show you these pictures in a minute. This is the visual, literal sampling and visualization from this Gaussian. But before going there, let me give you the definition of the general case if you need. So this X is what we talked about. Every coordinate is independent. And for now, assume they are centered at 0 and variance 1. This is your Gaussian multivariate. This is a vector. Okay, fine. Now you go take a matrix. A is a deterministic matrix. It's m times n. You multiply it with your random stuff. Now you get a new vector. And you can shift it to anywhere you like by adding and subtracting another vector. This way you could create a whole bunch of different Gaussians. And they're all still nice and computable Gaussians. They will look a little more complicated when you write them out. But since all these formulas are worked out and saved, you can compute with them, okay? So this is the general version of a Gaussian random variable with several coordinates. Take the nice one, multiply it with any matrix you like, shift it anywhere you like. This is your new Gaussian. And probabilistic PCA is something like this. So if I don't know if anyone had time to look at our notebook over the weekend and get creeped out with the eigenfaces, okay, that's what the very last one is something like this. I'll get back to that again. Okay, this is how it looks. If you write down the density, doesn't matter too much. The upshot is one thing that you need to understand from here is since you're multiplying with this matrix A, it was m by n. Okay. The covariance matrix comes out as this guy times its transpose. The covariance matrix is not identity anymore. You got some new covariance created by your matrix A. That's all you need to remember, okay? All right, that's multivariate Gaussian. Now let's do some visualization and have a sense of this. All this, definitions, it's hard to, at least for me, get an intuition of those. Okay, here is some visualization. Let's go step by step. I don't like how it rendered too much. Let me see if I can make it even bigger. And not bad, yeah. Well, okay. So let's first look at the first picture, then I'll look at the second one. All right. So this one is the case that you got something like an identity. Then you see you almost get like a sphere because every direction is the same. If your covariance is identity, that means every direction is treated the same. Sometimes you would see this thing called isotropic, okay? If your randomness is seeing all directions equal, sometimes you would also hear that word. I'm just telling you if you hear it, it's not something fancy, it's literally this picture, okay? Okay, that's covariance identity. This guy here, let's see. All right. So here you get something like a sphere, but the length of the axes is squeezed or stretched. This is the case that the covariance matrix is a diagonal. Let's say the first diagonal entry was 100, second one was a 1. Well, then the first direction will have a lot more variance. So this is what's going on in this picture. And the last one, if you are not diagonal, if you're any covariance matrix, you can also turn the thing around, squeeze and stretch from whatever direction you like. And this is how it is going to look if you plot something of that sort, okay? This is the density plot. And here, there's also contours and whatnot. And this corresponds to stuff upstairs. I think you can match the shapes. I don't need to explain it. This is that guy. They're literally plotting how dense is the stuff with 2D. Hottest here, coolest there, So, okay, that's how Gaussian stuff looks like in several variables. And that's the one that is used the most. Well, let me go to probabilistic PCA again. Yeah. So very good question. So here the transformation is this matrix A. And because I took this random variable, I transformed it using this matrix, and I also shifted a little bit. Now the question is what happened to covariance? Here it was identity. What is the covariance of this guy? And it's right here. You take your transformation, multiply it with its transpose, that gives you the covariance. Okay. Very good question. All right. Now let's keep going. Let me go back to probabilistic PCA. Now that we know the definitions more clearly, let's look at it from this angle. So I talked about this quickly in the end of last lecture. Let's do it, in a better pace this time. So what did we say? We got the PCA. What does it do? Well, it reduces the dimension of your data. That's it. If you give it some other data, you can get some nonsense out of it. If you ask the PCA, can you generate one sample from my data for me? It's not going to do anything for you. PCA is a good thing, but it does what it does. Okay. Now, what we would like our models to ideally do, first, we would like them to generalize, which means I created some model and I give it some new data it has not seen before. It should be able to tell me something reasonable about new data. That's what generalization means. Okay. And the second one, generation. If you can, you would be delighted if your model is also generative, which means ask your model to create a typical instance of your application and show it to you. That's generation. Okay. So the Gen AI is short for this. It's creating stuff for you. Like there was this deep fakes all over the place some time ago, right? I think they're not so common anymore. So they're generating literally a face that looks almost the thing, Okay, now we will have a very simple generative model off of these Gaussians. And it's going to go like this. You got your data and you picked your D. You're assuming that's like the real dimensionality somehow. And then in lingo, you will hear this D to be called sometimes latent space. Latent means hidden in Latin. The intuition here is like, I see 100-dimensional data, but in reality, it's controlled by just 10 dimensions behind. I just don't see them. That's the idea here. So this will be called latent space. And the thing living in that latent space will be called your latent variable. Okay. And then now our model is this. For now, I assume the latent variable that we don't see was a nice one. Gaussian, centered, covariance, just identity, like the nicest thing possible. And then my model is like, I'm going to take this guy. I'm going to do a transformation on it by a matrix and a shift. Okay. And then I'll allow some noise. This is not deterministic, literally zero. I am sampling some stuff around here. That's now my model. And I would like to fit the best transformation possible. So this gets close to your question. So what is the transformation? It is a transformation here. It's a matrix and a shift. And this is what I see conditioned on what I don't see. That's my model now, okay? Z, I condition on Z that I don't see. What I see, I'm trying to model it this way. I'm trying to fit the best model that has this flavor, okay? There will be errors. You're trying to minimize them. And then turns out if you go through the algebra, the best transformation is literally the transformation you have seen in your PCA, okay? So this matrix is those directions that we have seen in PCA. And the covariance is given by that matrix times this transpose. And since there is some noise here, it gets added. And this is literally what you see in the notebook, taking those image data and fitting in such a simple model. And what you get looking somewhat like a face is actually surprising. Okay. So if you look at the notebook at the very end, there's plots of this. And literally what it is doing is like taking those image data that is open source available, putting zeros and ones. It doesn't even have color. And trying to do its best to capture this, that's all. That thing having like a glass when you generate it is already surprising to me, okay? So this is such a simple generative model. Even this doesn't do too bad. And the illustration of it is right here. This is the illustration. This is your hidden one, like a Gaussian. And then you're transforming it with your matrix and shifting with this guy, putting it right here. This is what you will be generating when you sample. Yes. It is plus noise, but it's a Gaussian random variable. So it's not only just noise. We are making a very simple random variable assumption. That's why I was saying this is a very simple model. So this is your mean phase, this is your covariance, and you're fitting a Gaussian. You could have fit much more complicated random variables as well if you liked. Yes, go ahead, Farhan. Exactly right here. That's true. That's right. That's right. Exactly. So that's a very good point. That's exactly why some statisticians have currently called this sensible PCA. So they're saying in PCA, we already have errors when we measure, when we project, whatnot. So let's account for it with the errors with the noise we are putting here anyway. So very good point. So there are two sources of randomness. The fact that we're assuming there's a random latent variable behind, and also all our numerical point floating computations. They're just floating around here. Okay, so that's so far definition of covariance for multi-variable randomness. And off of it, we had a new interpretation of PCA, and we also got the probabilistic PCA again. We review it once more. Any questions so far? Yeah. PCA is deterministic. So latent only means something that is not visible to you. So here this Z lives in D-dimensional space. Let's say it's living in 5 dimensions, but my data got 1,000 something dimensions. I got this big image stuff, whatever many pixels you got. And in the backend, you're assuming there is something with just 10 coordinates. It's random and it's creating what I'm seeing. That's what latent means. Nothing fancy. Latin word for hidden. There is also that, yeah. But here, that's not what they're doing. They're assuming the latent variable is a simple thing. Yeah. This is our prior in statistics language. And our posterior is given by this relationship. And we're assuming I do a linear transformation and shift. And I'm trying to fit the best such model to my data. Exactly. Yeah. Very good. Any other questions so far? Because I'll tell you a little more about multivariate Gaussians. Yeah. You can do those. So one more step generalization of probabilistic PCA is called factor analysis. It's included in our textbook. If you want to go 2 steps more of generalization, it's called independent component analysis. You use tensors instead of matrices. You can do a whole bunch of different stuff. Yes. Very good. Okay, now, again, don't be scared of these equations. I did not write with my hand and literally took it from your textbook so that when you see it once again, you remember, yeah, I have seen this before. Because my handwriting may not look like what you see in the textbook. Okay, so, and the punchline is gonna be easy, I promised, okay? Don't worry about this. The punchline is easy. So you got a Gaussian with a whole bunch of coordinates, okay? Here, y1 itself has a lot of coordinates. Say, suppose y1 has 10 coordinates, y2 has 10 coordinates itself, okay? And together, they're a joint Gaussian. But y1 is a Gaussian itself, y2 is a Gaussian itself. Stacked together, they'll give you another Gaussian, but what are the relationships in between? So average of y1 and average of y2, if you stack them together, that gives you average of this new guy. That's kind of intuitive. When you look at the covariance of this new one, you will see covariance of y1 on top, covariance of y2 here, and covariance between y1 and y2 there. That's how it is going to look like. And here's how your y1 will look like alone. Average here, covariance this. Here's how your y2 will look like alone. In lingo, you will hear this called marginal. Since I copy paste from book, it's right here. Okay, they're called marginals. people introduce these words. Okay, not my fault. Okay. So if you forget, it's fine. But if somebody, I'm just trying to tell you words. If you go to a seminar or a business meeting, whatever, if you hear technical terms, so you're not scared. Okay. I'll be surprised if this comes up in a business meeting, but who knows? All right, let's come back. And then now, what is the posterior type stuff? What does it mean? Suppose I observed this part of my Gaussian. I have some measurements about it. Then what do I know about the first one after that observation? That's called conditioning on the second one. And apparently, that thing itself is again a Gaussian. Gaussians conditioned on Gaussians gives you yet another Gaussian. Okay, but the expectation and the covariance gets a little hairy, but it is known and recorded. You can just use whatever library you're using for it. The punchline is Gaussian conditioned on Gaussian is yet another Gaussian, where the expectation and the covariance are known equations. Okay, and then you might still ask, so what? Okay, I know Gaussian conditioned on Gaussian is Gaussian, so what? Okay, so I'll try to show you some applications of this knowledge. Yes, go ahead. Yeah, then here, this is 1, 2, because 1 is conditioned on 2. The other way around, you will get 2, 1. Yeah, but it's going to be a very similar equation. You'll just, yes, yeah, it matters, yeah, because, y1 could have, say, 5 coordinates, y2 can have 20 coordinates. They don't even have to be equal number of coordinates. So, question? You're good? Okay. Now, as I said, you might say, so what if I know this, what do I get out of it? So before I tell you what do we get out of it, let me remind you some basic stuff. Suppose we are trying to fit a random model with some parameters. Parameters here for Gaussian is mean and covariance. In general, this could be whatever parameters you're putting in your model. And you got some data. Okay, you have your data, it is D here, and you're trying to create a model of random variable that's supposedly fitting to your data with some parameters. Okay, and then what are our assumptions here? I don't necessarily know the parameters. I don't necessarily know what is the correct mean and covariance I have to pick to fit the best. I just know those parameters are there. And as soon as you say, okay, I think mean is 5 and covariance is blah matrix, then you can start computing what is the probability of seeing the data that you're seeing. That is likelihood of seeing the data you're seeing based on your assumptions. Okay, this is called likelihood. And how about if I don't know at all what are the parameters, can I try to go through all of them and compute the probability of the data I'm seeing? Yeah, this will be called, well, this usually can only happen in theory, though, going through all parameters and computing the integral, good luck, right? But this will be probability of seeing the data in whatever parameter that you can use in your model. You're going through all parameters, putting all the likelihood on top, integrating through them. This is PD, okay? Now, what we actually like to see is this one, though. I saw my data, I saw it. I'm trying to understand what kind of parameters are likely for me. That's what I want to understand. So this is called posterior. And by definition, this is, if you remember, joint density divided by this density. That was the definition. And joint density can be written using the likelihood as well. So that's a good thing, because this is equal to that. This can be also written using this times that. You see, it's the same thing, but this is much easier to compute, okay? And then this will be a constant, even though we don't know what that is. When I'm trying to find the best theta, I can only deal with the top. So even though this is a terribly hard thing to compute, usually it doesn't hurt you, okay? So that's like the overall structure. I got some data, I am trying to fit it with a model that has parameters here in theta. Parameters are here, data is here. This is likelihood. If I fix some parameters that I think are right, what is the probability of seeing the data that I saw? This is the posterior. This is usually what we're interested in. I saw the data. What is the probability of getting a certain type of parameter? The one that has more posterior probability is going to be the parameter you're going to pick. Okay, very good. Now let's see what, since we know all this stuff for Gaussians, normally this, I cannot compute for Gaussians, I can compute. I can do all this computation for Gaussians, and let's see what kind of thing I could get out of it. Yeah. All right, so one application that I find a lot of fun is called missing value imputation. If you tweak this a little more, this will be applicable in the version I showed you. It's going to be mostly for fun. So what is it? So this is a true matrix. Green and blue means plus and minus sign. And how big is the square? It means literally the number. So area of the square will be the number you're putting there, okay? And if it is blue, I think positive, green, negative. So this is a way to visualize a matrix. It's your data array. Then what do? We go hide some of this data. This is what you observe. Now, we are gonna use Gaussian priors and try to fit our best bet. This is what I know. This is the hidden truth. And I'm gonna go measure, let's say, suppose this is a vector. Now 1, 2, 3, 4 things out of it. This will be literally this y2 for us. And I know y1 conditioned on y2. Yes, go ahead. Yeah. Larger green means the more negative, exactly. So thank you, very good. Larger blue means more positive. Thank you, very good, fantastic. All right, so now in one of those columns, there was like 4 entries I saw. That's gonna be what I know. I'm gonna condition on it, and I'm gonna try to predict what's the rest of those entries in that column. The whole column is a vector, just like the thing on top. I know some of it, and I'm gonna guess the rest, assuming everything is Gaussian, okay? And then your model for Gaussian is this, right? Expectation here, covariance here. Then what would be your best bet if this is your thing? Well, you'll put the expectation, or you'll sample from it and put those in the stuff you don't see. And that's literally what it is done. And these diagrams are from the textbook. It is reconstructible. The code is, you just click the textbook, gives you the code. And this is literally what you get out of it. So by going from here with this Gaussian perspective, I'll get to that just one sec. This is what the code produces for you. And this is the truth. Not too bad. Okay. And of course, one issue will be color will be very hard for Gaussian, because it's say centered at 0 for a sec. Assume, I don't know if the mean is 0, but if it is centered at 0, -1 and +1 are equally probable. For Gaussian, negative or positive, it's gonna mess up there. But the magnitude, how big is the square, that you expect to do decent, okay? So far, so good. Any questions? So this is immediate application of using the fact that Gaussian conditioned on a Gaussian is yet another Gaussian. But I'm going to show you something more applicable next after this. Somehow I like this. It's fun. This Hinton apparently invented this visualization. You just look at colors and see kind of what's going on. I think this is, they call this guy godfather of AI or something. He is in the news all the time. Apparently this is what he used to do before he got cool. But, okay, now the next thing I would like to show you before I show the next application is, what if I got a transformation involved? The story goes the same. If your Z is this Gaussian, if your Y conditioned on Z is that Gaussian, and if you stack them together, and if you try to look at their posterior whatnot, you again get yet another Gaussian. And how you compute it is in these formulas. You can just code it up and computer can do it for you, okay? You don't have to assume 2 coordinates are Gaussian and Gaussian stacked up. You can even take a Gaussian, do a transformation on it, stack up together, then you would have conditional probabilities worked out for you. Yes. Yeah. So let's see, let's see how are we going to do it. The next application gets very close to what you had in mind, I think. So now you are trying to capture something unknown to you. Z is a matrix. That's the vector, I'm sorry, that you don't know. You're going to do some measurements on it, and you're going to try to estimate your best bet on this vector. You're literally trying to locate something. Let's say you got your radars or sensors. You got measurements. You're trying to locate something. Okay? All right. And then for now, since we have no idea about Z, you will go put a crazy prior on it. You'll put a huge covariance in some mean, let's say 0. Okay? So this is your prior on Z. Since I have no idea, put a huge variance. It could go all over the place. Okay? This is my prior. And then what do? I start sampling, and I start doing these measurements and getting some sampling data about this vector. So why I'm taking measurements, this a legitimate question to ask. Suppose your Z you're trying to estimate got a whole bunch of features. Let's say it's a 1,000-dimensional vector. Multiply it with a 5 times 1,000 matrix, your output will be 5. That'll be your measurement, for example. This you can do just for computing quicker. Okay. All right, very good. And I got some measurements. These are my data. And you don't have to do the transformation I just said. You can literally just take measurements about the location of your Z as well. Okay. This is how it is written here. I took my measurements. I'm expecting them to be centered around the actual correct thing I'm trying to estimate. And they will all have some covariance matrix, I'm sorry. This is the noise. You're taking measurements about the Z you're trying to understand. They're all noisy. Suppose they are centered at the Z, and they got some noisy covariance. Okay? Then what I want to do now, I want to first, again, Gaussian being nice, you compute through this whole thing, data posterior conditioned on Z, comes out to be yet another Gaussian. Okay, this requires a lot of work. It is done in the book, you don't need to do it. Okay. But then I would like to do the other way around. So this was data conditioned on Z. I would actually like to do Z conditioned on the data I'm seeing, because I'm trying to estimate this Z. And since we know Gaussian conditioned on Gaussian is yet another Gaussian, through your data, you just plug in the formulas above, the formulas you see here, or if you did not do any transformation, the ones you see here, you literally plug in those formulas, and it gives you your mean and covariance estimates for the Z. And here is something plotted. This was your prior. This is sampled data. You plug in those sampled data into your formulas, and they keep changing the location of the Z for you. And this is the end result you get out of it. You see covariance got much smaller. This means you're getting more and more confident in your estimation. And there is variations of this. Sometimes people try to estimate an unknown array of data. Sometimes they try to combine different sensors to each other, etc., etc. And all this is off of this like Gaussian, conditioned on Gaussian being Gaussian. Okay. Yes, go ahead. So. Sample variance is lower than the population. I mean, these are kind of somewhat different concepts. Here, we had no idea about the Z. That's why we put this huge variance. This may not be the real truth. So what you said is more applicable to when the real truth, the population thing is something, and then you're trying to estimate it through sample. That's our prior. So we're basically saying we have no idea. Let's put a huge covariance matrix there so it can go anywhere it likes. I have no idea what that is. And as I get measurements, I just update this Gaussian to Gaussian formula, it keeps changing the mean and the covariance matrix for me. No problems, no problems. And this is the end result of this process. Yeah. So far, so good. Yeah, it's hard to understand the order of, the author has a specific way of ordering. Yeah, I agree. So, and in the other explanations as well, if you don't notice, I would start from the spherical, then I would go to the one that is, he puts the spherical at the C, and then the one that is more complicated at A. I don't know. I'm trying to understand. I'm not sure. I don't see anything, basically. You don't know. I see. Let me ask this to our statisticians. I see them every now and then when I'm in the building. If, I'm not strictly Bayesian or frequentist. Statisticians are usually very picky about this. So let me ask a Bayesian statistician and see if they have an explanation for that. Okay. All right, very good. So far, so good. Now, wonderful. Okay. So now let's just remind the language once again. So I have my data D. I am trying to fit a model with parameters theta. This would be called likelihood. If I pick the parameters, what's the probability of me seeing the data I saw? This would be called posterior. If this is my data, conditioned on the data, what are the probabilities for the parameters to be picked? Yes. Data. Yes, I'm trying to say data. Exactly. Yes, D is data. Thank you. So now, yeah, D or even like something with a more curvy, yeah. So delta is, let me write this since we discussed, big delta is this, small delta is that. There you go. And my PhD advisor was Greek. As soon as I write alpha and A next to each other, he would go crazy because for him it's the same thing. He will be totally confused. When he sees alpha, he reads it as A. The other one also reads an A. And anyway, so now let's talk about maximum likelihood estimation. What does that mean? I got some model on top of my head, Gaussian, categorical, Bernoulli, binomial, whatever random variable I got on top of my head. I got some data, and I'm trying to pick the best parameters for my models. For Gaussian, it's going to be mean and variance. For Bernoulli, it's going to be the success probability of your unbiased coin, biased coin, whatever it may be. And then the definition goes like this. So they're the same definition. This is for discrete, this is for continuous. You can just think through this. You got the density at your data with the parameters theta you picked. And if you had n data points, you multiply all those densities. And you want to find the theta that maximizes this multiplication. The idea is I saw the data I saw. Now I'm trying to pick the theta that seems to maximize the probability of me seeing the data that I saw. That's what maximum likelihood estimation is. So every theta gives you a likelihood estimate. Maximize that quantity, find the theta that does this likelihood the most. Okay? So let's do some examples to make this concrete. So let's say my random variable was Bernoulli. I'm flipping a coin, it's biased. Heads, tails. I don't know how the bias is there. And that's what I'm going to try to fit. Okay? Okay, so suppose I got the samples, and then n samples there. If it was heads, you put a theta. If it was tails, you put a 1 minus theta. And this is the fancy way people write this. I don't like this, but you will see it all over the place, not my fault. Okay. So this means character function, yi being 1. That means as soon as it's a heads, put a 1 here. If it is not a heads, put a 0. When you put a 0, you ignore this part. Okay. Literally what you're doing is this. I flipped it. I got, say, 5 heads, 4 tails. Okay. Then hedge probability, theta, theta times theta times theta times theta. The number of times I have seen the heads, number of tails I have seen, 1 minus theta. That's what's going on, okay? Yeah, for example, if you have seen n1 times heads, n2 times tails, this is what you're gonna get. And now we are trying to find the theta that maximizes this expression. And now that becomes a calculus problem. This is your variable. Mess with it as much as you like. Make this thing the biggest possible. Okay? And since these exponents are kind of nasty, you take logarithm to make it look nice. So maximizing this would be the same as maximizing its logarithm. When you take logarithm, though, the exponents drop down. Stuff starts looking nice. Then you do your calculus, take derivative, put it to 0, you know. When you have optimum situation, that means derivative is 0. When you do all that, you get what you expected already, okay? So you would get the best theta to put is the number of heads you have seen divided by the total number of tails. Okay? So very intuitive, right? And then in the textbook, you would see maximum likelihood estimation done for whatever you want to see. Okay, Gaussian, Bernoulli, categorical, maximum likelihood estimation of linear regression. So I'll put the pointers on canvas. You don't need to know all these, but if you need, it's worked out written there. Okay. So, all right. And then let me see. Yes. Now though, very good. Sorry? This is for specifically Bernoulli, this flips. But your model could be a Gaussian, right? And it will be something else. Your model could be a different random variable, then it will be something else. That is very nice, yeah. But as I was trying to say, all that is worked out. You can look it up if you want to. But I want to show you a something that is important because different libraries use a different version of what I'm going to tell you. So it's good for you to know. You can check what your library is defaulting. If it did not change in the latest updates, for example, pandas and NumPy were defaulting on a different thing in the stuff I'm just going to tell you. So it's good to know what that is so you're aware of those defaulting stuff picked by the libraries. Suppose I'm trying to do Gaussian this time. And I got my samples. And what are my parameters now? Mean and variance. Okay, just univariate Gaussian. And if you got your samples, what would be your best bet on the mean? Well, sum them up, take their average. That's your best bet for the average. Okay. How about your best bet for the variance? Well, take your best bet for the average, put it as the expectation in your variance formula, take minus square, sum it up, divide by 1 over n. This is very natural, right? That will be your best bet for the variance of your data. Does it make sense? Yeah. Yeah, that's where I'm getting it. Okay. So far, so good. That's like take your data, take their average. That's my best bet for the average. You can, of course, work out this maximum likelihood estimation stuff. This will give you exactly that. Okay. You can do the calculus. It's what it's going to give to you. And you can do the calculus also for the variance. This is what it is going to give to you as well. And there's a reason for ask what he asked, and that's why I'm talking about this. Okay. Wait a sec. Wait a minute or two. We'll get there. Okay. Now, here's a little surprise. This I will give you an exercise, but if you take this quantity that is very natural, data minus my best estimate for the average, squared, summed, 1 over n. And if you take its expectation over all possible data points you could get, if you compute it, you don't get the variance of your model. You know, this requires, it's surprising, this you need to work out to see. Instead of, when you take expectation of this very intuitive thing, it doesn't give you back the variance. Instead, it gives you variance multiplied by n minus 1 over n, turns out. Okay? So this estimate, even though it's super intuitive, and that's what maximum likelihood estimation calculus will give to you, introduces actually a bias in your computations without you noticing. Okay, because this is not one, it's a biased thing here. Okay, if n is large, n minus 1 over n will get very close to 1, so it's not too much of a big deal. But it's good to be aware of that. And then the language people would use for this, they would say, if I have an estimator based on my data, I got n data points, phi n is my estimator for my parameter, be it mean, be it variance, whatever you're trying to estimate. Take its expectation. If in the expectation it's giving you back the true thing that you're trying to estimate, then it's called unbiased estimator. Okay. If it doesn't happen directly by expectation, but if it is happening when n is too big, your sample size is too big, then it will be called asymptotically unbiased. All right. And now, because this thing that I showed you, which was very intuitive, according to this definition, this is biased. The expectation did not give me what I wanted. It gave me what I wanted times a number. But since I know this number, I can, mess with it, right? So I can multiply it with n. I only got an n minus 1 divided by n minus 1. I can make it biased by force, basically. And that's what a lot of libraries do. Instead of this natural thing, they will multiply it with n over n minus 1 to kill this. And if you do that computation, it comes out this way. And that's probably what you saw before. That's why you were asking why there is no n minus 1 there. Okay. So this is an unbiased estimator. I have to check, but I think NumPy was defaulting on this and Pandas was defaulting on that. So just be aware which one the library you're using is using so that you don't get surprises if your n is small. If n is big, you're not going to notice it too much. It's just n minus 1 over n versus 1. If n is a million, that's very close to 1 already. Okay. Let's see if there is anything else I want to say today. I think that's probably more or less. Okay, let me wrap up in the last minute I got. So what did we do today? We talked about random variables that has many coordinates, multivariate random variables. We looked at their variance and covariance, and looking their covariance gave a new interpretation of PCA. PCA gives you the direction that preserves most of that covariance. And then we looked at probabilistic PCA again. Knowing this hopefully made it a little more easier to understand. And then we go into specifically Gaussian. We learned Gaussian, condition on Gaussian is yet another Gaussian. And for that, I showed you 2 applications for fun. And then we talked about maximum likelihood estimation. And now, one thing we did not address is like, if your model has many variables, how would I go do this maximum likelihood estimation? So if it is something known and cooked up, and if there's a formula, okay, maybe easy. But that's not always the case. So then how would I go about doing maximum likelihood estimation? The next lecture, I will start by giving you a nice example of this and some other stuff, as you can tell. Okay. So let me show you just a picture of what's about to come. The next lecture, I'll show you a particular algorithm called EM algorithm. That's a common heuristic used for maximum likelihood estimation. That's going to be starting point for our next lecture. And after that, we will do what's called decision theory. More or less now, this is the end of our probability discussion. Okay. Thank you so much. I can take